Okay, so in this video, we're going to learn about titration. Why do we do titration? We've heard about it a lot of times, but the main reason for doing titration is to figure out the concentration or purity of an unknown compound. So for that, we would need a solution whose concentration is known. So the idea is you would need these apparatuses for doing a titration. This one is a burette. This one is a burette. And then this one is called a pipette. This one is called a pipette. So, say this is the solution in a flask that you do not know the concentration of. So, what are you going to do? You need to figure out the concentration of it. So, you would say you take a specific amount of that solution using a pipette. So if this is a 25 cm cube pipette, so when you use a pipette filler, which is this one, it's like a sponge. So when you squeeze it, you dip it into the solution and you let it go and it sucks in the solution. So usually pipettes are fixed, but there are some graduated pipettes as well. So this pipette is always going to draw 25 cm cube. It has a graduation here, and when you fill it up to this, you have 25 cm cube of solution up here. So what you do is, with that unknown solution, you take, using a pipette, and then you transfer it onto a conical flask. This one is a conical flask. You have a photo of it here as well. So this one is the conical flask. The reason we transfer it to a conical flask is because we're going to add a known solution from the burette into the conical flask. So if you were adding it into a normal flask, it might splash out when you're swirling it, mixing it. So as it's narrow at the top, chances are less that you're going to splash it when you're swirling it and mixing it. So you have taken, say, 25 cm cube of your unknown solution here. Unknown as in you don't know the concentration of it. You have no idea about what the concentration is. But you know the volume. You have just used a pipette to transfer. You've just used a pipette to transfer 25 cm cube of that solution into the conical flask. So now say that solution was sodium hydroxide. Say that solution, the unknown solution is sodium hydroxide. So you have 25 cm cube of sodium hydroxide in here. So 25 cm cube NaOH, concentration, unknown. We have no idea. So what we do now is we know that sodium hydroxide is going to react with HCl and produce NaCl and water. If you're confused about why this equation is like this, it's a base, it's an acid, so it's a neutralization reaction. You're going to end up with a salt and water. So I know that the mole ratio, which is they call it the stoichiometric ratio, which means this is 1 here. That's why we don't write anything. If it was 2, then we would mention it. If we do not mention anything, it basically means there's 1. So what this tells us is 1 mole of sodium hydroxide is going to react with 1 mole of HCl to produce 1 mole of NaCl and, you guessed it, 1 mole of water. So we know that sodium hydroxide reacts with HCl in a 1:1 ratio. We'd call it 1:1 ratio. Good. So Now, as we know that sodium hydroxide reacts with HCl, what we can do is we can take a known concentration of HCl into this burette, and we can fill this burette up with HCl. This is filled up with HCl all the way. So, say for example, this is HCl. The concentration of that HCl is say 1 mole per dm cube. Volume, we'll figure it out using the experiment. Moles, we will calculate. Okay, so now what we're going to do is we're going to start the experiment. But before we start the experiment, what we need to do is we need to add something that's called an indicator. So what that does is, at this point I'm just going to talk about them briefly. So you add a suitable indicator. At that point, we just add a suitable indicator. Suitable indicator. So what this suitable indicator is going to do is, when you have the required amount of each of them, the required amount, that means that when you have the equal amount of each of them, the amount that's needed for them to completely react with each other is present. So I already have, let me change the color again. Okay, so I already have sodium hydroxide in the flask. So I have 25 cm cube of this, but I don't know the concentration. So I don't know the moles. I have no idea. And then what I've done is I've added the HCl in the burette. Its concentration is known, 1 mole per dm cube. So I think you have, I think you guess where we're going with this. So if we can figure out the volume that's required to have them in equal amounts in the flask, if we figure out that volume, it's very easy for us to figure out the moles using the second formula that we have talked about in the previous videos. So once we know the moles of HCl that reacted, we know that the moles of HCl that reacts is going to be equal to the exact same amount of NaOH. So then we can figure out the moles of NaOH in there, in the flask. So we know the volume of NaOH, we know the moles of HCl in the flask, so we can figure out the concentration. So we're just going to go through that. So once we have filled out this burette with 1 mole per dm cube concentration of HCl, we're gonna add a suitable indicator into the flask. Now let me recap. In the flask, you have 25 cm cube of NaOH that you have no idea what the concentration is. So I'm just gonna add a little bit here. What I'm gonna add is this HCl. You know the concentration of it. Any solution whose concentration is known is called a standard solution. So as you know, the concentration of the HCl, this is called the standard solution in this case. Standard solution. This HCl is my standard solution. So I'm going to use a standard solution to find out the concentration of an unknown solution. So after adding the suitable indicator, we'll start adding the HCl. So I'm not going to go into the details of how you perform the experiments because I'm just going to show the calculation at this point. So you keep on adding HCl and you have the indicator and NaOH in here. So whenever you'll reach a point that the moles of NaOH and the moles of HCl are equal, you're going to see a sharp change in color in here, and so you're going to stop so you're going to turn the tap and you're going to stop adding any more HCl into the flask. So when you shut down when you turn off the tap, so what happens is you can read how much of HCl you have added into the flask. So you know the volume now. So say for example you've carried out the experiment and the sharp change occurred. There's a sharp change in color when you have added say 25 cm cube. No, let's not say 25 cm cube. Let's just say something else. Let's see. Let's just say you have added 23. So when you have added 23 cm cube of HCl, you saw a sharp change in color. So I can figure out the moles of HCl I've added because I know the volume of HCl I've added, I know the concentration of that HCl. So using the formula that we have learned before, moles is equals to volume times concentration. So the volume moles of HCl added. So the volume was 23 cm cube, but remember we have to convert it into dm cube. So divided by 1000, it becomes dm cube. The concentration was 1 mole per dm cube. So your dm cubes are going to cancel out, and then you're left with, I'm just going to leave it in fractions. So you have added this many moles of HCl. So according to the equation, I know that this many moles of HCl reacted with this many moles of NaOH. Because that's why there was a sharp change in color. Because they were in equal amounts now. They were neutralized. So basically the indicator is going to give a sharp change in color when the solution is neutralized. So as the ratio is 1:1, I know that at that point NaOH, the sodium hydroxide, was also present in this much amount, 23 by 1000 mole. So my moles of NaOH in 25 cm cube solution is 23 by 1000 mole because they react in 1:1 ratio. So notice here I said moles of NaOH in 25 cm cube solution because this was the 25 cm cube solution. So it must be true that HCl only reacted with this solution up here, only with this 25 cm cube solution. So it must be true that the amount of moles present in that 25 cm cube solution is the same, 23 by 1000 mole. So now we know the moles of the NaOH. So originally we knew, so for NaOH, volume was 25 cm cube because we used the pipette, we used this pipette here, and we drew 25 cm cube of it and put it in the flask. So I have 25 cm cube of NaOH there, and right now I have just figured out the moles of NaOH. So which is 23 by 1000 moles. So now we need to figure out the concentration of NaOH. So using this formula, moles equals to volume times concentration. We're going to use this formula here, but rearrange this. So we need to find the concentration. So if we rearrange this equation, say this was the original one, moles equals to volume times concentration. So concentration is going to be moles by volume. But we need to be careful about the units. The units must cancel out. So in this case, not cancel out, but the concentration needs to be in mole per dm cube. So this is cm cube. So C equals to m by v, right? So m by v. So if I do it like this is going to be 23 by 1000 mole divided by 25 cm cube. So whatever this value is, the unit is going to be in mole per cm cube. It's going to be in mole per cm cube. So let's say this is 23 divided by 25,000. This is mole per cm cube. So if we want to make it in moles per dm cube, we have to convert the volume into dm cube. So the way we would do it is, everything remains the same, you just convert the volume unit. So this is this many moles. So this guy, we have to divide this by 1,000. So this becomes dm cube now. So the thousands are going to cancel out. This is basic math. So you have 23 over 25 moles per dm cube. So now you know the concentration of the sodium hydroxide. That's your final answer.